Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. Thank you for coming. It's my pleasure to introduce Diana Rosing from University of California, San Diego. She did her PhD from Stanford, and then went on to HP Labs, and then finally came on to San Diego, so she really likes California. So she's going to be telling us about how to build energy-efficient computing systems, and she and Rajesh, who will be visiting us on Monday, they're leading research projects in this apparently hot area. So,
thanks.
Diana.
Thank you all for coming. And yes, I do like California. Sunshine is great, but I also love hiking. And I think you guys have some of the best hiking around Seattle. So I come up here very often to satisfy my craving for woods. As you can see, I work on energy-efficient computing. I'll be spending quite a bit of time today talking to you about power and thermal management as it relates to both individual servers and multiple sets of servers. Some fraction of the time, I'll be talking about what happens inside of a processor and how that may change the decisions we make that go beyond. And then towards the end, I'll be talking about how some of the same energy management decisions can be done to change energy efficiency in sensor networks. It turns out that the ideas are actually quite similar. Numbers are very different. In data centers, you're talking about megawatts and millions of dollars. And in sensor networks, you're talking about milliwatts or maybe even microwatts, and probably not millions of dollars in terms of energy cost. But the bottom line is still the same. You need to deliver some results within a reasonable amount of time and as low energy consumption as possible. So the future, as we see it, basically is a world that has a whole bunch of different types of sensors around us and on us as well. And towards the end of my talk, I'll illustrate to you a couple of projects we run at UCSD to look at how our daily decisions will affect our long-term healthcare. So this is work that we do with UCSD School of Medicine. And that's focused primarily on preventative medicine, so not necessarily trying to deal with somebody who is sick. And the interesting thing you find when you're looking at preventative medicine is you need to be able to track effects on the health in 24/7, 365 days a year. When you try to do this, you have huge amounts of data that get generated, and you have a gigantic problem with battery lifetime. If you're trying to detect only a small event using sensor nodes and on a large-scale environmental installation, you can do duty cycling. So you can sample periodically with relatively low sampling rate. However, if you're trying to figure out whether a person is running versus sitting versus sleeping versus doing something else, you will need to be continually monitoring. And so energy is actually a very big challenge here. Secondly, there is a middle layer here that involves mobile access. So sensors are fine and well, except that sense data needs to somehow get to us in a form that makes sense to us. And today, most of us will use our cell phones to interact with the data. And in fact, in the project that, again, we did with the healthcare center, really showed the power of providing feedback to people through a cell phone. Those cell phones also have battery limitations. A lot of us have more sophisticated smartphones where we, take pictures, we get email, we may even watch some media. I got little kids who love playing games on them. So battery lifetime is really key. Also, the connectivity between sensors and cell phones and the back end is something that is variable. Sometimes we have good 3G coverage. At other times, when I was hiking on Olympic Peninsula, there was no 3G coverage. However, if I'm a heart patient, I need to be able to get connectivity to the sensors on my body, perhaps to the sensors in the environment, through that same cell phone. So there needs to be a way for us to adapt to what is going on in the environment and what is going on with the particular application and the user's needs. And at the center of this picture is a data center infrastructure core. So if we have all this data from the sensors, from the cell phones, all the data eventually will need to be stored somewhere, will need to be analyzed, and will need to be leveraged over time. So going back again to the healthcare example, we actually don't know what really causes asthma in people. We do know that there's a factor that's genetic. We do know that there's another factor that's environmental. For example, there was a study that showed if you live within a couple miles of a freeway, the study was done in LA County, as you might imagine, you have 50% chance higher of developing asthma. That's a huge number. The issue is that we don't know whether this comes because it's a freeway, because we happen to be testing a certain fraction of population that simply is more susceptible to asthma, because maybe there's some other environmental causes that would also affect asthma. It's not obvious. The only way we can get answers to these questions is by having large sets of data over a long period of time that can then be analyzed retrospectively, right? And you get that by having this large infrastructure core. So at UCSD, we're really lucky in that we have full-fledged deployments of both large-scale environmental sensor nodes. Work again with UCSD School of Medicine looking at body area networks. We have tight collaboration with people in industry, Qualcomm, for example, that's focused on developing cell phones and cell phone infrastructure. And we have a supercomputing center that deals with humongous data sets. So we can really find out what is involved from the outside looking in of this picture, and how does one achieve energy efficient computing across this big scale. So with that in mind, I'll zoom in on my small slice of this big, huge pie. And specifically, I'll talk about power and thermal management, starting from the data center infrastructure at the center, and work my way out to the sensor networks and mobile devices towards the end of my talk. So with data center infrastructure, there are two variables that I've really been concerned about that go beyond just simple scheduling for performance, and that is power and temperature. Power in terms of how much we're spending to actually run systems, processors, memory, servers, racks, and so on. Temperature in terms of what fraction of this power is actually going to cooling, and how will reliability be affected by the scheduling and by power management decisions that are being made. So with that in mind, I'll be talking first a little bit about some issues that make our servers not so energy proportional. And specifically, I'll be focusing on interaction between the processor and memory infrastructure. How could we make memory a little bit better architected so it doesn't consume as much energy as it does today? CPUs, it turns out, are actually fairly good already. You can scale energy fairly well. Then I'll talk about, if we have a particular system, what is the right way to monitor the workloads and based on the characteristics of workloads to do power management. So this would be both controlling sleep states and voltage scaling, and how those decisions will make a system operate more effectively. We'll be talking about machine learning algorithms that we've developed that are really good at doing online adaptation, and then how power management decisions affect thermal management. It turns out that the two aren't always compatible with each other. So if you think about large-scale servers, the absolutely best way for you to save power is to just not run a server, right? As soon as you turn it on, you're already consuming a huge fraction of the overall power budget. However, and this same idea applies to on the chip, right? On the processor core, you may have 8 processors, 4 processors, whatever it is. The best way you're going to save power is by shutting down the processor. Your next best way is to use voltage scaling potentially, or to be careful what workloads you place. However, shutting down this processor and having something else run very fast right next to it creates big temperature differentials, which can lead to reliability problems. So these two decisions aren't always compatible with each other, and I'll be talking about how do we actually balance the two to achieve both low energy computation and also to get good reliability at the large scale. And lastly, I'll talk about how we scaled some of these results to a virtualization system that runs at the container data center level that we have at UCSD, and some of the preliminary results that we got from that. And then, as I said, the second topic will be looking at wireless sensing and energy management, or better said, what do we do at the outer parts of my picture on the previous slide. So what happens with sensors and with mobile devices. So the high-level view of cost-efficient energy management in data centers is that you have some sets of jobs that are coming. They need to be scheduled. They need to be scheduled in a way that's going to meet performance requirements. So you got SLAs, you got response time requirements, maybe you have some throughput requirements that are necessary to meet the SLAs. That scheduling will make decisions on what racks and what servers jobs will run at. At the individual server level, you have either an operating system or a virtual machine that makes a decision on which exact processor something will be running at. Those decisions will strongly affect energy efficiency of the overall system. Right now, those decisions happen largely disconnected from a decision on what level of cooling are you using. So level of cooling is controlled by an independent set of thermal sensors. Granted, the temperature that's sensed by those thermal sensors is affected by scheduling decisions. However, we found if we actually consider both at the same time, we can get much more effective results. So at the high-level view, what we're really interested in is monitoring temperature, power, and performance at all of these scales, right? Using those variables to then control cooling, power states that we can control, and task scheduling. Because we believe that it's only if we start leveraging multi-scale properties of this system well that we'll get fairly big energy savings. The goal here is to get energy efficient computation. We have found that if we utilize some relatively simple prediction models, we can actually do even better than the current reactive policies. So what I'll show you is some of the results on predicting what temperature is likely to do in near future, where near future is defined as a certain number of scheduling decisions going forward, and what incoming workload is likely to look like, again, in near future, where near future is basically a function of the decision I have to make right now. Okay?
Are you only looking at controlling the racks, or are you also going to be talking about controlling the backroom, chillers, and all that? Well.
So the project that actually we have funded at UCSD involves a whole data center container. And we have control of the water that's coming in, the rate and the temperature. And then inside of the container, we have tapped into all of the controls for the fans that are in there. And we obviously have ability to schedule jobs. Now, we're not quite, so you won't see results of doing it at the whole container level because we're not quite there yet. We got this container just this last year. So we're... this is a Sun container. It's actually a big NSF project, NSF MRI grant that got us the container. So it's just within this last year that the container has been fully populated. We're at a point where we're running right now at 5 servers, and we're going to be deploying what we have tested already at small number of servers to the racks in the container. So it's going to be running at 7 racks within about a month. But to actually get to that takes a lot of work. So you won't see the results, but that is actually the end goal. And the project involves multiple people. It's not just me that's doing it. I'm leading the energy efficient effort here. So if we zoom in onto a single server, it really depends whose server you buy and what that server is designed to do. So the first server that we got was a really small 2-socket quad-core Xeon machine with only 8 gig of memory. So if you have a machine that has relatively small amount of memory, doesn't have the most powerful processor in the world, I mean, it's still reasonably powerful, the type of division that you can see when it's running active is about, maybe a bit less than half will go to the CPU. You have some chunk that goes to memory that's relatively small. And then you have almost 16% that goes to fans and very little that's going to hard disk. Now, if I start looking at the opposite side of extreme, and I don't have this picture here, unfortunately, but you can see the Google's server, that now CPU here has dropped down to about 30%. Memory is also 30%, because in Google servers, it's about 64 gig that you have, right? And then the other stuff is basically the rest of the pie. And if I've talked to people at Supercomputing Center, they actually have some of the servers that run at 512 gig because of the types of jobs that they need to run. 512 gig of memory gets very, very hot. And there, a huge fraction of the pie goes to memory and to fans in order to cool this down. So the picture, my point here is that things will change drastically in terms of what slice of the pie it is, but the top components that are consumers are usually CPU, memory, fans, and power supply and efficiency. Power supply and efficiency I will not be talking about at all. I think there are people who have done a great job of designing better power supplies, and it's just a question of, are you going to spend the money to put it in? What I will be talking, and I won't spend much time talking about CPUs. Intel seems to be doing an excellent job designing energy scalable CPUs. I will talk a little bit about how I use the properties of those CPUs to achieve energy efficient computation. What I will discuss next is what we have started looking at in terms of novel memory organizations to try to deliver the same or near the same level of performance at a fraction of the power cost. And also I'll be talking a little bit later about what happens with temperature and therefore with cooling system control. Yeah?
I have a question with your testing. When you talk about the distribution of this power, did you load hard disk CPU in full capacity at the same time, or just based on statistics?
No, so that's a very good question. And I'll show you a slide, and it changes.
For database, data storage server.
So this server is not...
This I/O is right.
I totally agree, and I do not show that here.
Okay.
This is not the database storage server at all.
Computing server.
So this here is a computing server. So the picture, really my point with these pictures is that the slices of the pie change drastically. Right? So for the hard disk, you're right. If I was focusing on storage servers, I would actually need to have the last bullet that says, how do we deal with the hard disk?
The most expensive component is the storage server.
Yeah.
And typically, storage disk is most expensive. Mm-hmm. So that's why.
So one of the things that you might be interested in that we are doing for another big grant through SDSC that I'm a part of is looking at large-scale supercomputing storage that includes flash as a front end. Because that turns out to be one of the good ways to get the efficiency that you need and the response times that actually those types of applications really need. Yeah. Okay, so what we've looked at in terms of memory design is the idea of using both non-volatile and volatile memory combination. The problem with DRAM is, yes, it responds very quickly. It has pretty high density, so you can pack a lot of stuff in it, but it also costs a lot of power. So if you look at a typical server, you turn on the server, that memory is going to be on for the rest of the time that the server is on. And that really doesn't make server very scalable in terms of energy. The problem with using non-volatile memory like PCM is that, yes, if you can turn power off to it, so the data is retained well, so you can achieve much more energy scalable computation as a result. The problem is you can write to it only so many times before it fails. And the other side note is that it's not exactly mainstream yet. It's getting there. So the challenges are to be able to hide these drawbacks of PCM. Main drawback being the write endurance, which is a very similar issue that you have with flash. So the design goals are for us to uniform distribute write access across PCM, so do varileveling much in the same way as you do it with flash, except now it's at the main memory level. It's not as the cache to the disk. And to direct any write-intensive applications to DRAM instead. So we achieve this by doing a combined hardware-software design. So this requires some changes to the operating system, and it requires changes to the hardware. On the bright side, the overhead actually of the changes to both is very, very small. And the benefits, as you see, may justify the approach. So at a high level, what we have is a new memory controller that then monitors the writes and monitors the varileveling properties of PCM. And based on that, will direct workloads appropriately. So here's how it works. It looks at, so I'll have two different types of memory. I'll have DRAM and PRAM. The data and commands come through the memory controller. The memory controller actually has a small access map cache. So by different pages, and this is done at page level because page is a unit that you allocate from the operating system, you actually count how many writes have been done. Based on that write count, we can figure out whether that page should be retired and a new page brought in or not, because that then allows us to do write varileveling. And obviously, when a page gets to some threshold of writes, we have to be able to swap the page. So that is where the interrupt for page swap occurs. And as we reach the limit of PCM endurance, we may have a bad page interrupt. So at that point, that interrupt is issued and a new page again is allocated. So the objective is to uniformly distribute this writes across PCM. We do this by holding within memory allocator 3 different lists. One is a free list on the left, and then threshold free list on the right. With the free list, it's basically a set of pages that have not yet been allocated by any application. As the applications come in, they allocate the pages. Once those pages have been allocated some threshold number of times, they get put into a threshold free list. Eventually, you get to the point where free list is empty and threshold free list is full. At that point, you swap the two. So the threshold free list becomes empty, the free list becomes full, and you start allocation again. You do this enough times, you'll get to the point where some of the pages will go beyond the write endurance per page. And at that point, the page will go into the bad list. So that is where this bad page list comes. Page swapper will handle page swap and bad page interrupts. Bad page interrupt obviously will mark page as invalid and hopefully avoid failure.
For typical applications, what's bad page list?
So this swap threshold actually is a variable that we've played with some to see for a set of applications within benchmarks that we had. And it turns out that it's actually not that sensitive. So we had swap threshold in the paper that we published this last year. It's a new year already. Set to 1,000, but it turned out if you put it down to 10, you get almost the same result as you put it up to about 5,000 writes. So interestingly enough, it's really not that sensitive. There are two policies that we looked at. So one policy is what we call uniform, that basically says when you reallocate a page, you always want to put the page into PCM. The idea behind that is PCM is lower power, so therefore you'll be more energy efficient. However, clearly this could be a bad policy because PCM also has very slow response time to a write, much slower than DRAM, and you'll get to getting your page to become a bad page sooner. The next policy that we have is a hybrid policy that actually after passing the threshold, we'll allocate the page instead in DRAM, assuming that because this page has been used so much, it's likely being used by an application that has lots of writes and therefore should be going into DRAM. So we used baseline system that had 4 gigs of DDR3 SDRAM, and this actually was measured on the server that we had. All the results that you'll see with PCM are simulated because we don't have that much PCM in-house. So the hybrid system had 1 gig of SDRAM plus 3 gigs of PRAM. So it was about 1-to-3 ratio, and the uniform system was all PRAM. The workloads that we simulated had sort of a set of different types of applications. The idea was that we wanted to see both the percentage of reads, percentage of writes, and the total number of pages vary significantly. So we selected applications that would represent different classes of workloads by these particular values. So you can see that the AppLu, for example, has lots and lots of pages and fairly high write percentage. And that on the other end, 6-track, because it's so CPU intensive, really doesn't do much. And face recognition is somewhere right in the middle of the two. So average overhead in terms of performance for the hybrid system was about less than 6%. This overhead is largely due to the fact that writes take longer in PCM. So if we actually had a better caching methodology, we could probably hide this overhead even better. The overhead of the uniform system was much bigger. It was about 30%. So you really wouldn't want to build a server with just PCM. And that should be kind of obvious anyway. But there is real benefit to, and I'll skip through the details here, to actually combining PCM and DRAM. So if we combine the two, you get energy savings of 30% without considering power management. So we did not actually turn off power to PCM and use the fact that it retains data. So I think the overall energy savings can be much bigger than this 30%. This is in the worst case, effectively. You have a question?
The 6% is just the total time to execute the application?
So it includes all of the overheads in it.
What do you mean by the overhead?
Of access map analysis, so trying to figure out what is the number of writes that you have to that particular page, and for the page swaps. So overall performance overhead, basically, is included. what your application would experience if it used this new system.
What's the estimated mean time between failure for the PRAM in that scenario?
The number we had used was 10 to the 9th writes. It was a number we got out of literature. As number goes up, our results get better.
What I mean in terms of the amount of hours of use or whatever based on...
Oh, so with the particular, and there is actually detailed discussion on this in our paper. This was analysis that we had to do because otherwise, if a server dies within 5 minutes of you using it, it's useless. So it turns out that if you have a dumb policy with 10 to the 9th writes, you can end up with a failure within about an hour. But if you have a smart policy, like what we've designed, you end up with a failure of about 10 years. So you have to be very careful what you do with your software and hardware.
That's quite the difference. Do you...
Yeah. Well, the difference comes from the dumb policy basically will allocate write-intensive page, always the same page at the same location, and therefore it dies quickly.
Just
Yeah.
one area.
Yeah.
It's very hot.
Yeah.
Did you look at the concept of potentially persisting what was in the PRAM between OS restarts?
See, that's what I mentioned here at the end. We have not accounted for that in this energy savings. What my student is working on right now is estimating and evaluating how well would we do if we actually leverage this idea. Because I think the savings will be much bigger, and it will enable you to wake up extremely quickly. You have instant on, effectively. And the fact that we use relatively little DRAM and PRAM, is another issue. Normally you would want about 1 to 10 ratio between the two to get even bigger benefits. But to actually simulate 1 gig to 10 gig of PCM is very difficult to do with simulators. We had hard enough time allocating enough memory to fill up 4 gig in a simulator. So that's one of the limitations of doing it simulation-wise. But jointly with Steve Swanson, we're building an evaluation board system that will have memory controller in an FPGA, and we'll actually be able to see in somewhat real life what happens. Any other questions on this? So the nice thing about using PCM in the way that we've talked about is not only that you can now retain the state, but we can also think about having a completely non-uniform memory architecture. So we can have chunks of PCM associated with chunks of processors, and therefore you can start actually creating a truly energy proportional computer, right? Because I can assign workloads in such a way that only a fraction of the memory is being used instead of all of the memory is on all the time. Even though maybe to the application it looks as if all of the memory is there, simply because the data is still retained. It just isn't on because you're not currently running it. Okay? So that's actually the motivation behind going with this work. Okay, so going forward, as I said, we have this great NSF-funded Project Greenlight. The idea is to first evaluate the energy efficiency of a larger scale installation, and we're interested in seeing literally what happens at the whole box level. So how efficient is it if I do X versus Y in terms of what is the cost to power the box and what is the cost to cool the box? And those two variables on this box are very easy to measure because I got one plug for water and one plug for power. So it's pretty much instantaneous feedback. In order to achieve more energy efficient computation, we look at two classes of algorithms, power management and thermal management. Power management, because obviously our goal is to lower the energy consumption. Thermal management, because lowering the energy consumption of just the powering aspect of it would not necessarily be the best thing for the cooling system. So we need to be able to balance the two. And I'll show you some instances of why this would be the case on the chip level. And this actually applies also to the server level just as well. So first thing that we did is we started looking at workloads. And this was actually done ages ago on a single machine. And what we looked at is different devices within the machine. So you see on the top a hard disk trace. On the bottom, you see wireless network interface trace. The reason why I included these two is because they're about different from each other as it gets, right? On wireless network interface, you have relatively fast inter-arrival times, and you're expecting actually to have very low power consumption. On the hard disk trace, you expect much slower inter-arrival times and much slower processing times, and you also have much higher overhead for changing power states. The interesting thing that we found on these traces, what you see on the x-axis is the inter-arrival time measured in seconds. What you see on the y-axis is the tail distribution. So effectively, it's 1 minus cumulative probability distribution of getting that amount of inter-arrival time. The reason why I plot a tail of the distribution is because it highlights what happens with longer inter-arrival times. Why do I want longer inter-arrival times? Any ideas? Why do I care? Sleep, right? Or slow down if it's a CPU. When do I care about short inter-arrival times? Performance, right? So if you think about performance, people actually usually will use queuing models to evaluate performance of a distributed system. That queuing model does an excellent job at short inter-arrival times, i.e. when you're looking for high performance, and you can see that even here, that actually models for exponential distribution, which is the backbone of queuing theory, and heavy tail distribution, such as Pareto, really matches reasonably well experimental data. The problem is when you go to the right of this picture and you start looking at long inter-arrival times, the match is very poor. You end up in a situation in which exponential distribution makes decisions that are way too optimistic. That actually, in the case of a machine that we implemented, the policy that was based purely on exponential data, we ended up consuming more power than just leaving it on all the time. So this really illustrates that you really need to be able to model the workload accurately if you're going to do power management well. And in case of these particular devices, you see that the same conclusion applies. Regardless of whether you're looking at a hard disk, you're looking at wireless network interface card, you can look at large-scale networking data traces, you'll see exactly the same conclusion. It's all heavy-tailed. Why do people still use queuing theory? Well, it's easy. And it works reasonably well at those short inter-arrival times. Why we can't use simple queuing theory for power management is because it leads to bad decisions at those longer inter-arrival times. So that is what we did. We actually took a simple queuing model and we expanded it to ensure that we can model the points of time when we need to make a power management decision correctly. So when we're in the idle state, we can either wait and get jobs that we then process. Notice in these states, we're at the fast end of the curve where Markov model will hold. Once we get back into the idle state, we have a decision to make. That decision is, do we do something? Do we slow down? Do we shut down or not? If we decide to shut down or go into sleep state, it takes us some amount of time to get there. So this cannot be modeled again with the Markov chain. It has to actually be modeled with a uniform or some similar distribution to uniform distribution. Essentially non-exponential because it takes you a finite amount of time to get there, right? Similarly, as you saw on the previous slide, the request that comes after longer idle period, you really want to model with non-exponential distribution. You need heavy-tailed model. So you effectively have two distributions that actually govern the decision. And this is exactly where we had to make a little more sophisticated model. So what we did is we went with time-indexed, that's what TI stands for, semi-Markov decision process. It's basically a glorified Markov chain, a little more complicated. The assumptions are that general distribution governs the first request arrival. So this is the arrival that breaks the long idle period. Exponential distribution can be modeled for everything else. And user, device, and queue models are stationary. That last assumption is actually the lousiest one of them all. What does stationary mean? It means that on average, the statistical properties do not change of the distributions that I've designed for. And that we know to absolutely not be true at a typical set of servers. However, if we can pretend that it's true, you actually get globally optimal policy with simple linear programming, and you get results that we implemented that are within 11% of an ideal policy. This ideal policy knows the future. So you get really good result. So the question is what do we do about the stationarity assumption? How do we handle that? Yeah?
Is the service time exponential or heavy-tailed?
I didn't hear you.
The service time. How did you model the service time?
That's a very good question. So the service time that happens down here was modeled exponentially. So we assumed once the request comes, that's a beginning of a set of requests that you have to process that happen relatively quickly after each other. And at that point, we're back into this red part of the picture. Yeah. And that turned out to really not affect things much. If you have different results, it would be interesting to see. But it really didn't affect things much. It was really this decision of, do I go to sleep or not? That was a critical decision. Yeah. So what we did to deal with the stationarity is we said, instead of designing one single policy that does a great job for all of the workloads, except it's not optimal for anything, what we want to do is have a library of maybe a small number of policies, each of which is really good at delivering savings for a class of workloads that we can select among. So that is how we used online learning here. On the bright side, we're able to measure pretty good energy savings. We had experts. This is effectively policies that can control power states and can control the speed of execution. Each of these experts was specifically optimized for a class of workloads. So for example, you would have web search policy, or you would have a database policy, or you would have, whatever, video decoding policy, because these workloads do have fairly different properties from each other. And then we have a controller that monitors what's going on in the system. It monitors it by looking at hardware performance counters. So it doesn't necessarily know anything from the application. If it knows something from the application, it will do better, obviously. It selects the best performing expert. This would be whatever it thinks is the best policy. That particular policy makes decisions for a device, and then we evaluate. How well were these decisions made? How do we evaluate? Well, it's fairly straightforward. If it has to do with going into sleep state, you know exactly how long the idle period was. So you can figure out what was the best decision to make. And relative to that best decision, you can figure out how well did your policy do. So if it was a simple timeout policy, it would wait some amount of time before going to sleep. That amount of time that it waited is counted against it, right? The really cool thing about the controller is that its performance converges to that of the best performing expert at a very fast rate. So it's very good at selecting what is the best policy to run right now. That rate is a function of the number of experts n. Now remember, we have relatively few of these experts. We're not going to have hundreds of them. A few to well represent classes of workloads that you have running, and the number of evaluation periods. And this, in case of the operating system, would be scheduler ticks. Okay? So here are a couple of examples of results we got on the hard disk drive and on a processor. For the hard disk drive, we're looking at different traces that I got from HP. So my days of working at HP paid off. I picked 3 different traces because I wanted to see traces with fairly different average interarrival times and different variance around that average. We wanted to show how well we can adapt. We looked at hard disk because decisions that are not correct for the hard disk showed the worst possible case, right? Because this takes so long to respond. And on the CPU, we're focusing more on voltage and frequency scaling. So on the hard disk, we had 4 policies that were implemented. There was a simple timeout policy, that's a default. There was an adaptive timeout, our policy that was optimized for specific performance overhead. So in this case, it was optimized for 3.5% performance overhead. So the nice thing about actually, that I forgot to mention about these policies is this is the only class of power management policies that can be designed to meet performance guarantees. So you can say, I have this performance guarantee that has to be met. It'll output a set of decisions that will minimize energy within that performance guarantee. And the last one is a predictive policy. Now, this was just a sample set that represents what we've seen in literature. You can add whatever other policy you like. Within this sample set, you can see that our policy was best for performance because we obviously optimized it to be that way. And that in this particular case, predictive did really well with energy savings. Now, when we actually ran across all of these different workloads with our online learning controller, you find that we can fairly easily trade off low performance overhead. And in that case, our controller will pick our policy here most frequently, because that is what gives you low performance overhead, with higher energy savings, and it'll pick the appropriate policy for that. Okay? Similar thing happens when you look at voltage scaling. So in this particular case, this was actually done for a cell phone type application. And you can see that we have 4 different voltage and frequency settings. And as we trade off low performance overhead for energy savings, you can see that you get better performance if you run faster, obviously. And then as we want more energy savings, we're going to spend more time running at low speed. However, what you notice for this particular application, quicksort, there's a good fraction of the time that we also run at 400 megahertz, even though we're maximizing energy savings. The reason why this happens is because quicksort has regions in which it's more memory versus CPU intensive. And our controller is able to detect this appropriately and select the correct setting to ensure that you get performance and maximize energy efficiency. Because if you're CPU bound, you're not saving energy by running slow, right? So that is effectively what you see here. 25% of the time we're CPU intensive, 75% of the time memory intensive, hence about 75% of the time you run low, about 20% of the time you run faster. So that brings me to the last question, that I almost always get asked when I give this talk, and that is, you get these great savings in multi-scaling when you run on an old CPU, effectively older technology. What happens when you do this in servers? And the answer actually is a little depressing. So I wanted to share that with you. This was a set of results that we got by running AMD Opteron machine. We also did the same thing on the Xeon. The results are compatible with each other. So the conclusion that we draw out of this is a correct conclusion. Presented this to Intel. They agree that that's where things are going. You can see for Opteron, the range of voltages at the top speed is from 1.25 volts. At the lowest speed is 0.9 volts. So there's very small range, actually, that we're playing with here, which by itself already tells you that the amount of energy savings for slowing down is going to be much smaller than it is for processors in the older technology. In the contrast, for the X-scale processor, I think the range is from 1.2 to 1.8 volts, which is much bigger, 0.6 versus not even 0.3. Versus the range of frequencies, in this case, from 0.8 gigahertz at the low end to 2.6 gigahertz at the high end is huge, right? That's more than a factor of 4. Compare that to my previous slide, the range of frequencies was from 200 to 500 megahertz. So that's about a factor of 2.5. So basically, you would expect X-scale to get better energy savings with voltage scaling just by looking at these numbers than AMD Opteron, for sure. The other depressing thing about this processor, as compared to older X-scale, is that it leaks like crazy. So leakage power in these things is about 45%. So what this tells you is that as you slow down, about half of your power is simply going to be wasted 4 times as long if you run at the lowest frequency. That is very bad news. In contrast to that, X-scale, I think we estimated it about 20%. There's a big difference between 20% and 45%. So we wanted to illustrate the point. What we're doing here is we're comparing slowing down. So if we run at top speed versus at one of these lower speeds with 3 simple power management policies. The top policy, all of these 3, will have results where we run as fast as we can, and then we switch CPU to state C1, so we just remove the clock supply. This is the lightest sleep state that you can choose. Then we switch CPU to state C6, so it's completely off. This is the deepest sleep you can do with the CPU alone. And the last policy actually says, well, this is great, but what about the rest of the system? CPU can sleep, but there is a whole bunch of other stuff that's still on. So in this case, we put memory to self-refresh to show how does running as fast as you can and shutting off actually help the overall system power, and to contrast that to slowing down. Okay? So here are the results. These results actually show you only a small sample of workloads. We specifically picked MCF because it's very memory intensive, 6-track because it's very CPU intensive. So this will show you approximate range of savings that you can get. You would expect MCF to give you the best savings because of its memory intensiveness. So slowing down CPU actually should not affect its performance as much. Versus for 6-track, you would expect to get really bad results because slowing it down will affect performance and energy. You can see, first of all, if you look at the delay column, that at very best, at the top level, the percent slowdown is about 30%. And this is running at 1.9 gigahertz versus 2.6 gigahertz. So you're paying 30% of performance overhead for almost no power savings. Okay, so the power savings here, what we're showing here is percent energy saved for voltage scaling relative to running as fast as possible and going into C1 state, running as fast as possible going into C6 state, or putting memory in self-refresh. Okay, so your benefit for voltage scaling is relatively minuscule. On the worst end, you have overhead of 230% in performance for 6-track for about 7% benefit for voltage scaling. So how many of you are going to do voltage scaling? Yeah.
Because they're totally incomparable. When you're doing voltage scaling, the processor is still running and able to process requests. When you put it to sleep, it's not.
Yes, and that is true. Now, why are you doing voltage scaling?
Save power.
So what this shows you is you're actually not saving energy. What the reasons why you may want to do it.
Is that a characteristic of the processor you're using, though?
It's a characteristic of all of the high-end processors you buy today. There is no processor that you can buy on the market that I know of today that would show significantly different results here. If you ran on your cell phone, you would see different results because it's older technology and obviously much lower performance. But for energy savings perspective, it actually does not make a lot of sense to do. It does make sense to do for power perspective, power budgeting, right? Voltage scaling will lower your power budget instantaneously while allowing you to continue running. It also makes sense to do if you're desperate, right? You need to save the last bit of, so in case of thermal management, if things are getting hot, you still need to run, but you need to run at a way that lets you not be too hot, you're going to use voltage scaling, right? So if you actually talk to Intel, their newest processors that they're looking at putting out on the market going forward are going to have much faster in and out of sleep states than they ever had before, and are going to have a lot less flexibility with voltage scaling because they don't see voltage scaling as all that useful. So paradigm is really changing. The other thing to think about is, in the old times when we had a single processor, the idea of using voltage scaling made a lot of sense because, as you said, you can still continue running. If we shut it off, nothing is happening, so you can't continue getting results. With lots of processors, you have the option of continuing running, perhaps running even faster if you use the top speed, while at the same time perhaps shutting off 1 or 2 processors on the die to save energy. Yeah?
That's actually just where I was going to go, shutting down the processors. And in doing
you don't have to shut off everything, basically. You can
Right.
shut off 1 out of 8 cores.
And if you do so, is the control for that being done in a way where you eliminate the static leakage as well?
Yes. Yeah. And that's why these numbers look the way they do. Yeah. Because basically you have guard transistors that turn off connection to the power supply. Otherwise, it wouldn't work. You would have the same problem. Yeah. Okay? So that brings me to the key points. You saw that having power management policies that understand workload characteristics and can adapt to them can make a big difference. You saw that lowering voltage and frequency settings doesn't necessarily help in high-end processors for pure energy savings. However, it does help with peak power reduction. It does help with thermal management, and obviously for systems that don't have high leakage, it's still a very good option. So if you have a system that has low leakage, by all means, I would use it, which is why you see voltage scaling still very prevalent in all the mobile systems. So this brings me to thermal management. It's pretty clear by now that the picture is not complete if you don't think about temperature. So for thermal management, what we took as inputs is workloads that we collected at data center. This was work done jointly with Sun Microsystems. They, turns out, have big reliability lab right next door to UCSD. And there they have access to all the workloads from their customers. So that's what we used. I have a student who worked for Sun. We took floor plan, and based on that floor plan and temperature sensor data, we're able to figure out how to schedule workloads. What you see on the picture here is Sun's Niagara chip. That's what we started out working with. And one interesting thing that you should immediately notice is that on this floor plan, where you put the workload will affect temperature. If I put something that's very hot right here, it's not going to get nearly as hot as if I put it in the middle, because level 2 cache acts as a very big, huge cooling mechanism, right? The same is the case at the server and at the data center level. Where you put the workload in a rack or in a box will really depend on how well it can be cooled. So it's exactly the same concept that you see on chip that can be expanded to the whole box effectively. For power management, we used sleep states and we used voltage scaling. We also used the ability to migrate threads as another knob to deal with the temperature issues. And the results you're going to see are results that come out of thermal simulator. This is primarily because Sun wasn't too keen on releasing reliability data. But the conclusions actually hold. There are two classes of policies I'll show you. One is optimal and static. The goal behind this was to see what is actually the ultimate benefit for temperature if, first of all, I optimize job allocation for minimizing energy only. So if I say I want minimum energy, does that solve the temperature problem? Right? Secondly, what if I also add thermal constraint? How does that change things? So that is the top two policies. The reason why I looked at the optimal is because that tells me what I should be striving for with my heuristics. Obviously, optimal results are simply not possible in reality, where I'm doing online scheduling of large number of jobs that I don't know ahead of time. And this is why all of the operating system schedulers are heuristic in nature. So dynamic ones used load balancing, which was basically default that we had in Linux and in Solaris. This balances the threads for performance only. Some of that balancing actually helps temperature, some of it doesn't. Then we enhanced it by the information about the floor plan. So if now the scheduler knows that some cores are inherently likely to be cooler than others, simply because of where they are, it's going to do a little better job of allocating based on that knowledge. The next policy that is a simple improvement over the coolest floor plan is a policy that uses thermal sensors. It says it keeps information on recent history per core of what temperature has been, and depending on how hot it's been, it'll give either higher or lower probability to send workload there. So if it's been reasonably cool, then it's going to have higher chance of getting new workload. If it's been reasonably hot, then it'll be lower chance. The idea behind this is to actually try to smooth out thermal gradients. So there are a number of ways that things can fail. One way that things fail is because temperature gets hot in a particular location, in a hotspot. There you have electromigration, you have dielectric breakdown. There are a number of failure mechanisms that depend only on what is the absolute value of the temperature. The second way that things fail is because temperature changes in time a lot. And this is essentially a stress mechanism. So if it goes between cold and hot a lot, you end up with failures. The last way things fail, which turns out is the biggest pain of them all, is what we call spatial gradients. So if across the die you have large differences in temperature, signals will travel at different speed in one area of the chip versus in the other. And you can end up with these nasty bugs to debug. These are not permanent failures. They're basically temporary failures that you can recover from, but they're horrible to deal with.
What kind of redundancy do you have in the sensors?
That is a perfect question. So sensors, to date, have been really lousy, actually. And in fact, on the original chip, we had one sensor that was very bad. So what we ended up doing is putting the chip in an oil bath to get an IR camera so we can actually see what temperatures were. Newer chips have more sensors.
Affect the temperatures as well.
Yeah, I know. But what are you going to do, right? What's the choice? The good news are that some of the most recent chips are coming out with a minimum one sensor per core, and that actually turns out to be good enough. If we have one sensor per core, plus we have information about the floor plan, the thermal properties of the package, we can in fact filter out bad sensor data. And if you're interested in that, I can show you, afterwards, some of the work we've published in this area. And this work, in fact, was done because we had all this pain with the single sensor on the die.
Is this something Intel and AMD are doing?
Yes. Yeah. So it's actually fairly well known by both Intel and AMD and Sun, who also has thermal sensors on the die, that those thermal sensors actually tend to be fairly low quality. They have very low A to D conversion, so they tend to be very inaccurate. They get very noisy data, and you have to calibrate them. And calibration turns out to be very non-trivial. So you can be really far off if you don't do this right. And that actually is even more true for servers and racks. So as we talk about these scheduling policies, they're closed-loop scheduling policies effectively because we monitor sensors, we monitor the workload, we make a decision based on that. and then we try to adapt, you really have to be careful, to identify sensors inaccuracies, to smooth them out, or to simply detect that something has failed and work around it. Otherwise, you end up with crazy decisions. You can, for example, one of the things that had happened was we ended up having a fan that kept spinning up and down a lot because it was triggering off of a sensor that was actually bad. So, okay. So moving on. The last set of policies that I'll show you are going to sleep when it gets too hot, slowing down when it gets too hot, and moving threads when it gets too hot. And then at the bottom, I have exactly the same policy we did for power management, online learning, that selects among these policies online as necessary. Okay? So first, the optimal. So this plot shows you the percentage of hotspots across the particular die that I was showing if we use load balancing versus if we do optimal energy-aware optimization. Now, mind you, this is a very small number of jobs here because doing an ILP for lots of jobs is impossible to get done. And then if we do thermally aware optimization. And what you find that's interesting is energy-aware optimization actually will create quite a few hotspots. It does give minimum energy consumption. So among these three, this is by far the minimum energy consumption. But it's at the cost of clustering jobs. And the reason why it clusters jobs, again, is because from a processor perspective, it's much more efficient to shut it off than to run it slower. Okay? So this, I think, should fairly well illustrate to you that doing energy management without considering the cooling, thermal, and reliability aspects is a bad idea, because you end up with corner cases that cause a lot of problems potentially. Okay? So here's what happens, again, if we now consider all different possible options and if we use online learning to select among them. So default is the default load balancing. And this was actually results done on Solaris. We ran all of the workloads on their server. So the performance is all actual performance running on the server. The temperature numbers are all simulation. Migration, so if you move a thread, if it gets too hot, power management, voltage scaling and power management, the adaptive random technique that I showed you that keeps track of temperature history per core. And you can see that this little adaptive random technique actually is a pretty good benefit. If you combine it with voltage scaling, you get to the point where you're very close to voltage scaling results, but not at the performance overhead of voltage scaling. And then online learning, which beats the best possible policy by 20%. The reason why it beats it is simply because it's adaptive. So it will select whoever makes most sense at any given point in time.
Are you going to talk about the impact, the reliability impact?
Yeah. So I'm not going to show reliability numbers because, again, I was not.
Whether you reduce the hotspot 20%, why do I care?
You care because temperature is exponentially related to mean time to failure. So if I reduce temperature by 10 degrees, the hotspot temperature, there is an exponential relationship between that and your mean time to failure due to electromigration and dielectric breakdown.
I understand that, but is this extending? I mean, I need servers to last me 4 years. Is this making it last 20 years?
So that's an excellent question. So this particular set of results, and I could show you estimates that we have for reliability. We can actually extend in this case, per core lifetime by about, a factor of 10 approximately by doing things right, at the cost of not saving as much energy, right? So you get the performance, you get the reliability, you get some energy savings, but it's not as good as you could by, doing it this way. How that affects the whole server, that's a whole another question, and that answer I actually don't have yet. The problem with all of this data is that it's very hard to get reliability numbers out of people. So temperature numbers I can get pretty easily, but what is exact relationship between the temperature differentials, and reliability, that's much more tricky. Yeah.
So let me flip this around the other way. Now that you've reduced the hot spots, normalize the temperature across the die.
Yes.
Can you now push the entire die harder?
Yes, and see that's what was at the behind this whole thing. Because effectively what we've done is we've created a more balanced thermal environment, which means that now we can actually raise the envelope. So we have more headroom to add more jobs effectively before your cooling system has to kick to a higher gear.
Or I would look at it another way. Let me run in higher ambient temperatures.
Sure.
Yeah.
Do that too.
So that
Exactly.
Yeah.
get all the info.
And the two are obviously directly related to each
You
other.
don't have to worry about peak.
Yeah.
Fundamentally.
And actually, it can get better than this. Because temperature is a slow-moving variable, we can do proactive thermal management. So instead of waiting for things to get hot and then doing something about it, we can in fact forecast that it will get hot, and based on that, allocate jobs so it doesn't get to that point. So it lets you work with whatever thermal ambient temperature you happen to have in the best possible way, effectively. So it says if I have X number of servers with Y number of cores, here's how I'm going to pack jobs in those cores so that the temperature remains within the envelope that I'm targeting. So for this, we take, again, data from thermal sensors. We used autoregressive moving average predictor. The reason why we used this predictor is because a simple exponential average did very poorly for corner cases where temperature cycled a lot. So if somebody decided to be really smart and save power and shut off the server and then turn it back on a lot, exponential average died on that. The nice thing about ARMA is you can also calculate it online very easily. So you can monitor, fit the parameters, and you can monitor how well it fits the results. And then based on this temperature, we actually do prediction. For some number of times in the future, number of scheduled instances in the future, what will happen, and based on that, we'll then schedule. Online, we monitor ARMA model, we validate it, recalculate if necessary, and move on with the decisions. So when we add this capability to the system, here's where we end up with in terms of reducing hotspots relative to default load balancing. Okay? So you can see that we reduce them by over 80%, over 60% as compared to reactive migration at practically no performance impact. So simply because, again, temperature does not change that quickly. So we leverage that. And similarly, gradients are reduced to less than 3% in terms of space and to less than 5% in terms of time, right? So you end up literally in a situation in which you have fairly flat and low thermal profile. That is nirvana of a reliability engineer. Okay? Yeah.
Do you have data that compares the temperature coming out of a server that's using thermal balancing versus one that isn't? I mean, is it actually detectable? You're using a...
I have data that compares multi-socket temperatures, and that definitely is, there's a big benefit that we've measured.
Like a degree or two, or what's the scale here?
It's not really a fair question.
It depends on what you're running.
Well, it's
Power of
actually
the server.
absolutely no. So I'm just like in any given. I mean, pick your configuration. I don't know what it is, but so what sort of differences were you seeing? I'm just trying to understand what the scale of this is.
So in the best case, we've seen about 10 degrees lower on the die, which is actually a big deal for reliability. But this is the best case. If you really run CPU-intensive jobs and all of the cores, and there ain't nothing we can do about it. We're stuck. So in that case, what he mentioned, slowing down is about the best as it's going to get. Maybe your performance isn't stellar, but at least your server hasn't died yet. Yeah. Yeah. So the other thing that we have done that I haven't included here is we looked at combining proactive scheduling of jobs with doing fan control. So if I have 2 or X number of sockets and fans that are associated with those sockets, they're trying to cool them, those fan speeds, turns out, are a cubic function. So power of the fan is a cubic function of its speed. So basically, as you go from low to high speed, you consume a lot more power. So you have a lot of motivation if you're already running at a higher power level at one socket to pack in as many jobs as that level of blowing air will handle. So when you do this jointly, we actually got savings of about 80% on joint socket and fan power, which is fairly big. And it's relatively simple to do. I mean, it requires from operating system to tap into thermal sensors and to have some level of fan speed control. Thermal sensors you can already do. I mean, we've done it, so you can do it. The fan speed control is trickier because right now that's done with an online controller processor that's on the board. So that you have to make some deals with manufacturers. But it's certainly doable. They can expose the variables that are needed to you. And the benefit, as I said, is big enough to where it may be worthwhile thinking about it. And if it's if it's that big on a single server, I would imagine that you could get even bigger benefits at the whole box. So that's kind of what we're after right now.
You could probably just have a simple equation which said, well, okay, this fan is already running at high speed, so just pack all the jobs on there anyway. You don't really need to control the speed of fan.
Well, but it also goes the other way, right? You can also have a situation in which you've packed the jobs, you have more jobs coming in, so the question is, do I put it on that particular socket and possibly trip it over the control point, or do I put it on some other socket, and which other socket should I choose? And if I'm starting to get overloaded on a set of sockets, how do I offload? To whom? Right?
Also, in fact, other components in the server as well, which you have to monitor.
Yeah, so my student has just submitted a paper that looks at also memory subsystem. Because depending on who built the server, they may have put fans in such a way that they blow first across all of the memory, and then nice hot air comes to your CPU. In some cases, they actually build big air ducts that will take subset of fans to CPU, and the other subset goes to memory. So it really depends, who did it and how they did it, and the end result of your job scheduling will change drastically depending on what configuration is there. So what you really want is to be able to learn this online and adapt to it, which is why you want to have the controls and the monitoring capability. So for that, as we move from single server or few servers to multi-box level, we started using virtualization because it's a lot easier. So we developed the system that we call vGreen that's on top of Xen. The system is able to monitor all different virtual machines and the physical machine properties, communicates that to a general scheduler. So there is a server that right now does centralized scheduling across multiple machines. The idea is to do allocation of what VM should go where, and to also do power and thermal management in tandem with that. For workload characterization, right now, the results you'll see are very, very basic and rudimentary. They basically say, is it CPU intensive or is it memory I/O intensive? And depending on that, we'll locate it on an appropriate place. The interesting thing is that even this simple variable actually gives you good results already. So, after I saw that, I told my students, boy, we got to push the envelope here because you're guaranteed to get low-hanging fruit in no time at all. So that's what we're doing. So here's a motivating factor behind this. So we all know that because machines, when you turn them on, they consume a huge amount of power just being on. And really the major dynamic component is the CPU, right? So CPU will really affect the top range of power. Most people therefore assume that CPU utilization is good enough for estimating the power consumption of the whole server. And, to a rough degree, it may be good enough. However, what we found is, depending on what applications you run, you can have actually a pretty big range of the overall server power that you measure. We saw, here I'm showing 65 watts. We've seen up to about 80 watts, depending on the server, of delta without any power management, just depending on what applications you run. Okay? That tells you that smart location of jobs will actually make up to 70 watts of difference, right? So that is exactly what we did. We used a combination of spec and parsec benchmarks, 2 servers and 1 centralized scheduler server that's separate. And all we did is dynamic workload characterization and migration. And what we got is 15% AC power savings. So this is the whole box server savings with 20% speed up. So both performance and energy benefit. Yeah.
Do you have them packed together, or this is?
So this actually shows the same job, basically increasing the utilization. So if I have MCF, I'm going to run it on 1 core, on 2 cores, on 3 cores, up to whatever cores and threads that I have available. And it shows what happens there. On the next slide, it's actually mixes of jobs.
Are you doing VP capping on those?
Do I do what?
The virtual processing utilization capping to achieve the 25%? How did you control the 25%?
Oh, yeah. We basically capped it artificially because that way, we can control. Because, how are you going to create an experiment, right? Yeah. So really what these numbers should tell you is that there is actually a lot of potential benefit that hasn't been exploited here yet. When you combine the ability to characterize jobs, to collocate them appropriately, and then to do power and thermal management jointly. So going forward, I'm actually heading a fairly big center that's called Music, and the particular aspect of that I'm focused on is leading an effort on energy balanced data centers that spans from software to system and down to platform. And basically, we're looking at how we can do multi-scale, plus-layer, distributed, and hierarchical management. So the question is, where should the control sit? There are lots of different layers, and how should the communication happen between these layers? We want to ensure that energy is spent only when and where it's needed instead of wasted in lots of interfaces. Okay? And this brings me to a quick summary, which I think I can skip. And I have a few more minutes to maybe touch on some of the sensor stuff. But I think what's interesting about the sensor stuff is that all the ideas that I just talked about, minus thermal management, pretty much apply.
We're actually starting to talk about thermal management in these as well.
So, yeah, I guess if you have really bad environment, your CPUs have problems. And
we're not there yet, but it's
well, so the work that I have been doing that I haven't talked about at all is looking at heterogeneous multi-core processors that go into base stations. And thermal management there is actually a big deal. So I have a couple of papers that recently came out on that you might be interested in. Yeah.
Just one comment. This is a concern I've had as we do more and more management of
Yes.
different systems. What work, if any, and we've actually seen failures in servers as a result of incompatible controls where you reach oscillations.
Yeah.
So what work, if any, have you done in that area?
I've done quite a bit of work for the multi-socket, multi-chip. Have not done anything on the server level. The work that we did with multi-sockets actually looked at fan failures and oscillations, so designing policies that actually are stable across multiple variables. We are going in that direction. The problem that I'm running into is reliability has been difficult to model. So if you have data, that can help me do a good job of modeling, that would be good. I know.
Data center.
No, I totally hear you. We know.
And end up fighting each other.
Yeah, yeah, and that is why, when I said multi-scale, that's exactly what I'm after. You have all these different things, and they each individually could be designed to do a great job, but you put them together, you can have catastrophic failures. How do we avoid these catastrophic failures? And so I don't have a good answer yet. But we have started, in my case, we started kind of small, and we're starting to build up from there. And I also have a part of my team that started sort of from top down, so getting all the thermal data real time, trying to understand how it relates to the current control loop for the data center container, because there is already a controller in there, right? And if we make changes to that controller, what happens? Which is a scary thought. So on sensor networks is very much a distributed problem also, except in this case, it's also physically very much a distributed problem. So what you see on this map is a large-scale sensor network deployment. UCSD is this little dot right here that gives you an idea of the size. The range inland is about 100 miles. The network spans up to Salton Sea, just beyond Salton Sea. It goes 70 miles off the coast. The connection off the coast was done jointly with Navy, because they were interested in using our wireless backbone. It reaches close to Mexico and goes all the way up to Riverside County. What you see on this map is only the top layer of the network, so the wireless mesh backbone. What's underneath every one of these dots are literally hundreds of sensor node cluster heads and thousands of sensor nodes. And these sensor nodes do all kinds of different things, most of which have nothing to do with computer science at all. In fact, probably the largest density of nodes is for seismic monitoring. Scripps Institute of Oceanography deploys this. We have a number of ecological research stations placed that do things like temperature, water quality, soil. We have also people who are monitoring wildlife, so California Wolf Center. Lots of different applications. What I find really exciting about this deployment is exactly this, that it represents a real-life test case scenario of what is life going to look like as we start using more and more sensors and as people who are not engineers start deploying and using the networks. This network actually has also been used for helping California Fire Department fight forest fires and, in San Diego area. So the last big fire a few years back leveraged our network to a pretty big degree. A lot of the images that you saw came actually from our sensors out in the field. So here is an example In the very low end, I mentioned we have these earthquake sensors. They don't produce that much data. They're about 5 kilobits per second worth of bandwidth per sensor. However, they are somewhat latency sensitive when something exciting happens, where something exciting is defined as a big earthquake, right? So at that point, you really want this 5 kilobit per second trickle to make the 100-mile trip over a gazillion hops very quickly. At the middle layer, we have things like motion detect cameras and acoustic sensors that basically, in case of motion detect cameras, you can see the wolves here. They want to turn on when some interesting animal happens to walk by and then continue reeling the video while the interesting animal is still there and then stop. At the same time, we want to collect acoustic data. So people that are studying wolf behavior want to know, if this particular howl, if you really come close, you can see the howl on the acoustic sensor. How does it correlate with particular body posturing that the wolf is making? So you will need to have time correlation between these two, because these two actually aren't physically at the same location even. They're in a slightly different location because of noise. Okay. High-resolution still cameras, I give that example primarily because it's actually a lot of data that comes out of those. Wildfire tracking cameras, day and night. So these are still images of actually video cameras. They're strategically located at places that help us track how the fire is progressing. We have also done experiments with helicopters with cameras on them that then stream video to mountaintops and to the back-end control of California Fire Department. And then at the very high end, there are two observatories, Palomar and not Livermore and not Lowell. It's an L observatory, sorry, I'm spacing on it. But basically two observatories. Palomar Observatory produces, we allow them, better said, to put 150 megabits per second at night. So you can see a small problem. If I have 150 megabits per second in the middle of the night streaming through my network, and at the same time there happens to be a fire out there somewhere close to Palomar, there will be a problem in how quickly the fire data is going to get through. So we need to be able to adjust our quality of service settings along the network very quickly and easily. At the ultimate low end, we have devices that don't even use batteries. So this is an example of a structural health monitoring device that my group developed that actually uses solar cells and supercaps. The reason why we went this direction is because people like Los Alamos Laboratory that's funded this project want to deploy the sensors in areas that are very difficult to access by humans. And shelf life of a solar cell and a supercap is longer than a battery. The problem when you have solar cell and a supercap is that your power source is very unreliable. Sometimes it's really good, sometimes it's really lousy, and yet you need to be able to deliver results regardless of how bad it is. So in this, and for this particular application, it's actually doing what we call active sensing. So each one of these boards, which actually has been shrunk significantly, has access to 16 PZTs, piezoelectric devices. Each one of these piezoelectric devices can generate a wave signature that's sent through the structure and sensed by another one. So you can create pairs of paths. The signature looks something like this. The red line shows what's actually sensed. The blue line is how it actually should be if everything was okay. So you can see clearly that there is a problem here. Per single path, we get 10,000 samples. 16 PCTs, each path 10,000 samples is a lot of data that you can get, right? That data, as you can see, has to be processed. The type of processing that's done on this is very similar to what you do for video decoding or any other kind of large-scale signal processing. As a result, we had to put the DSP on board to really do this effectively. Now, clearly, this processing is significant enough to where during the nighttime, I won't be able to do a whole lot of it. During the daytime, when it's nice and sunny, I love San Diego, you can do a lot, right? So this picture actually shows a variability in amount of sunlight that's available and a prediction that we developed to give us an estimate of how much we're likely to get. Yeah, I see it. Yeah.
How often do you need to do this?
I'm sorry?
How often do you need to do this?
So that's the good news. A couple of times a day. Yeah. Unless something bad happens. So bomb drops, airplane runs into a building, earthquake happens, then you need to do it more. Right, but so on the bright side, it's not often, on average. On not so bright side, there are events that get triggered for which you need to be ready to respond. So you have to have some reserve planned always. And in case of solar, And you need to be, what we wanted to is be able to trade off the amount of accuracy for computation with the amount of energy that's currently stored and that's likely to become available. So that is exactly what we do with the predictor and what you see down here. That at some point in time, we execute very few tasks. At other times, we execute lots of tasks. So you can see accuracy grow significantly depending on how much juice we got. Okay? It doesn't, but it can estimate it by what it's currently getting out of the solar cell. So basically what it does is it says, well, currently I'm getting X amount of energy. Given the recent history, which it keeps, I predict that I'm going to get Y amount. And it turns out that for about 30-minute time period, we can be within 10% accuracy, which is really good enough. Because a typical, if I did all 160 paths, it'll take me about 3.5 minutes to complete. So 30 minutes is good enough. Okay. So going back to my original sensor network, you saw that at the top level, I have this high-speed wireless mesh. At the middle, I have these sensor node cluster heads that collect the data from a whole bunch of sensors at the low end. The sensor node cluster heads is where a lot of significant computation happens, and where also decision on who gets what data will occur. So there is actually quite a high demand for delivering reasonable quality of service with good battery lifetime. And for that, we developed routing and scheduling algorithms that helped us save power while improving the throughput, because we thought that this was actually the layer in which energy will become very critical, and that has not been addressed yet. And that enabled us to start thinking about combining body area networks with the environment. So for this new CitiSense project that I talked about a little bit earlier, what we're looking at is how do we monitor people 24/7 in order to understand how diseases such as asthma develop in the first place. And for asthma, you need to monitor air quality, you need to monitor physical movement of a person, so you understand how much physical exertion affects the breathing patterns. You need to monitor a whole bunch of parameters. And for that, we've actually already had a small deployment. What you see on this picture is results that we got by just monitoring physical activity. And we actually had 63 patients use our system with the goal of becoming more physically active and therefore losing weight. And it turned out that the simple job of monitoring it and providing quality feedback in real time through the cell phone, motivating people hugely. People really loved the system, and they actually lost significantly more weight than the people who didn't use. So in this case, it was over 6 pounds more than the control, right? Which is a big deal for 4 months. The most important thing, I think, from this came because over 95% of the people wanted to continue to use the system after the study was done and wanted to buy it for their friends and family. So people actually really liked what they got, which is not a small thing to do when you give real-time feedback on somebody's physical activity. It can be very annoying, if you don't do it right. Think about it. So this is why actually we got thinking, if we combine this with the environment, we can get a truly powerful way to provide doctors, medical professionals, public health officials with tools that they can use to understand what to do, and how to encourage us. Unfortunately, as you do this, you end up with increasingly more complex sensor networks. So you got stuff on your body, you got stuff in the environment, you got these, what we call local servers, basically cell phones, you got the back end. And to date, most people basically said just collect the data and then send it to the back end, have the back end figure it out and give you the answer. If you think about healthcare, that absolutely does not work, right? You don't always have wireless connectivity in the first place. And secondly, you got all this great processing right over here. Why are you not using it? Wireless actually costs you a lot of power in the first place. So that is what my group has been looking at, is if we have sets of tasks that have dependencies between them and that have some performance requirements. So I need to provide feedback within some amount of time. What is the right way to dynamically schedule them across this whole network in a way that maximizes perceived battery lifetime per user, because that's what you actually want. You want each individual to be happy. You don't really care about the whole system. And that delivers information that people need. So here's an example of a very simple task graph and that we may be working with. And we did 2 different types of binding. Again, the ILP, back to my slide some 20 slides back. The goal was to minimize the maximum energy consumption rate among all of the sources. So in that effect, we would balance how quickly you're draining batteries per individual user's perspective. And we got an assignment that was on average 20% better than moving everything to the back end in ideal conditions. So assuming you have perfect wireless connectivity, nothing changes, same tasks, you're going to do better if you actually assign some of the computation tasks to local nodes than if you send everything to the back. Now, if you look at the real life scenario, where you actually have to start from some initial assignment, detect that things are changing, and then adapt on runtime, here, we can actually get about 80% longer battery lifetime than the best static implementation. So we take the ILP result, we put that on, we are 80% better by doing simple online heuristics. Okay? So that's kind of where we're going forward. You can see that in my group, we're looking at everything from ultra-low power sensing systems all the way to large-scale servers. The idea is the same across this whole spectrum. We want to get energy-efficient behavior with reasonable performance. And we want to do it in a way that's relatively simple to verify and that's reliable. So that's all I had for you, and I think I just ran out of time. So this is good.
Well,
Thanks.